Picking up where we left off, we had been discussing some basic properties of groups. I'd been planning to make this video a little sooner, but I had family in town, was installing some new noise cancellation stuff in my apartment, and was staying busy with work. But yeah, let's pick up where we left off. Um, so if you're not sure, now's a good time to review the contents of the previous video before continuing. We kind of left off by discussing the fact that the order of bracketing in this product doesn't matter in groups. Value doesn't depend on bracketing. And again, that's like a good exercise in induction. You would call this maybe like a generalized associative property. Or a generalized associative law, maybe. We can also, on the topic of induction, we can define powers of elements in groups. So let G be a group, and let X be an element of the group. And let N be some integer. Then we define X to the N to be, well, based on our intuition, it should be like X times all the way up to this, N times, when N is positive. If N equals 0, well, we want to define X to the 0 to just be the identity. And if N is negative, well, then this should be negative X times negative X. Or I guess really it should be X inverse times X inverse times X inverse, again, N times. Or the absolute value of N times. And this is if N is negative, of course. That might be like kind of obvious that we would define it that way, but I think it's worth mentioning. We generally will let 1 denote the identity of a group. So I'll make a note. We'll often write 1 instead of E for group identity. Sometimes we might write 0 instead, but that would be like, especially if the group is abelian. So let's prove another property that we can do a nice type of algebraic manipulation in groups. And this is that we can do cancellation. So, and say we have like AX equals AY for some non-zero A. And just thinking in terms of like the real numbers here. What can we do? Well, we can cancel out those A's. And we can do a similar thing in groups. So let's define what we mean. Let's let G be a group. Then the equations AX equals B and YA equals B have unique solutions for X and Y in G. Also, and this is where the cancellation part comes in, the previous part is just saying that we can do a basic manipulation. Also, AU equals AV implies that U equals V. And similarly, UB equals VB implies that U equals V. Note when I make a U, I kind of give it this little like flare um, to help identify. And we can call the first of these left cancellation, because what we're thinking intuitively is that we're canceling out the A on the left. Um, Similarly, the second one is right cancellation. So that should make sense. Let's just grind through the proof real quick. It's not hard. Maybe I should use more than 2 colors in a video. All right, let's start with AX equals B. What can we do here? Well, we want to isolate X, right? Um, yeah, what do we do? Well, we know A has an inverse. So it seems natural to left multiply by A inverse. I'm not going to bother writing brackets because we know that they don't really matter in groups. And then A inverse times A is just 1, or E, whichever notation you prefer. So 1x equals A inverse times B, but 1x is just x, of course. So you can do a very similar thing for YA equals B, except now we do it on the right. So YA, A inverse, equals B, A inverse. Cancel out A times A inverse. Y times 1 equals BA inverse. But Y times 1 is just Y. Cool. And how do we know that these are unique? Well, it follows because the inverse of an element is unique. All right, let's actually prove the cancellation laws. So now say that AU equals AV. Got to give it the tail like I promised. Otherwise, I really don't like using U and V together. Well, then what we can do, we multiply on the left by A inverse. And then let's just run through this. So in particular, both of these become 1. 1U equals 1V. But remember, multiplication by 1 doesn't change U or V. So we get U equals V. So we can do the left cancellation. Right cancellation is pretty much identical. But the important thing to note, we really do need to be careful when we say we multiply on the left by A inverse here. Because remember, we never stipulated that our groups are abelian, so we can't use any sort of commutativity. That is, in general, A inverse AU is not the same as AUA inverse. So we really need to be careful in groups when we talk about which side we're multiplying on. Unless, of course, the group's abelian, then you can rearrange terms however you like. Okay, that wasn't a hard proof. I'm going to give 2 definitions that are actually maybe a bit confusing at first, but we will see that they are naturally related. And that is the definition of order of a group and order of an element. So let G be a group. If G is a set, because remember there's like an underlying set along with the operation, that's what makes up a group, is finite, containing exactly n elements, that is, there are n elements in G and no more, we call in the order of G. we say that G is a group of order n. And we might write this absolute value sort of G equals n. This is like a pretty common notation for cardinality, so it shouldn't be too surprising. We would also say, in this case, that G is a finite group. If G is infinite, though, say that G is an infinite group, or a group of infinite order, and write this. I don't know why I always include the plus in front of that. I picked it up from an old French mathematician, I know. Now, so this is the order of a group. So for instance, I'm not finished with the definition, but just as an example, the integers under addition, of course, are an infinite group. And the integers mod 5 is a group of order 5, because remember, this consists of 5 congruence classes, 0, 1, 2, 3, and 4. So nothing too crazy here. Now, though, let X belong to a group, and let M be the smallest natural number and remember, by the natural numbers, I mean the set containing 1, 2, 3, 4, 5, etc. In particular, I don't consider 0 to be a natural number. Let M be the smallest natural number for which x to the m equals 1. If it exists. It might not exist. We haven't shown that it exists, and indeed sometimes it doesn't. Should such an m exist, call it the order of x. And write absolute value x equals m. If such m doesn't exist, write, well, what do we write? Order of x equals infinity, and say that x has infinite order. Okay. So it could be a little confusing if you've never seen anything like this before. In particular, we're using the word order in two senses here. So it's really important to be clear. The first sense we mean is the order of a group, which is just the cardinality of the group, essentially, or the number of elements in the group. The second is the smallest power that you can raise an element to get the identity in the group. So when we talk about order of a group and order of an element, these things are actually different concepts, but it turns out they're actually closely related. So there is a good reason. We'll discuss this in more depth when we talk about cyclic groups, but basically the idea is that given a group element, its order, well, you can generate a subgroup of a group. I know we haven't defined subgroups yet. Oh, apologies. But you can generate a subgroup from that one element just by taking its powers. And we'll show that soon. And it turns out the order of an element is actually the order of the subgroup generated by that element. So that kind of explains a link between these two concepts. But for now, we'll just put a stopper on this. We'll explore the connection more soon. when we discuss cyclic groups. Okay, so just a couple of examples. If a group element has order 1, then X is the identity. That element is identity. Similarly, if X is the identity, then X has order 1. So really this is an if and only if statement. In the integers under addition, what's the order of 0? Well, 0 is the additive identity, so it actually has order 1. Doesn't that look weird to write based on like elementary algebra? But it's true. Um, and what about if X is a non-zero integer? Well, it has infinite order. Oh, not included in, not equal. Um, so take 1 for instance. No matter how many times you add 1 to itself, you're not getting 0. Similar for -1, no matter how many times you add -1 to itself, you're never going to get 0. Of course. So nothing too crazy here. Let's give like a really simple example. Simple-minded example. And this is like a really quick exercise. In the integers mod 4, compute the order of 3. We can brute force this one. So in particular, note that 3 is not 0. 3 plus 3 is 6. But we're doing this mod 4, so we can reduce to 2. Let's keep going then. We're trying to get 0, right? 2 plus 3 is 5, which is 1. And then 1 plus 3 is 4, but that's just 0. So the order of 3 is 4 in the integers mod 4. That was a pretty simple one. Now, one more generality on this section, and that is that if we have like a really small group, we can make a multiplication table. It's often called a group table or a Cayley table as well. And this isn't really something you do too much because, you know, if you were like think about making a multiplication table, it's fine when you're 5 years old and there are 5 numbers on each side, but would you really want to make a table containing multiplication information about 300 different numbers? It would be huge and not particularly useful. But let's let G be a finite group. And order the elements somehow, G1, G2 up to Gn, n being the number of elements in the group, of course. Well, we can make a group table as follows. Just like a multiplication table. Yeah. So this one will be G1 times G1, G1 times G2, G1 times Gn. In each space, we take the product of these two elements, G2, G1, G2, 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 GN, and then GN, GN. One particular thing to note is that if you have a really small group, something you can do is you can actually test whether that group is abelian based on the multiplication table of the group. What you do is you look for symmetry along the principal axis. If it's symmetric across the principal axis, then your group is abelian. You can see like how we would have that, right? So for instance, G2 times G1 would have to be the same as G1 times G2. So that's not surprising. And also, note that every element has note that every element has to appear exactly once per row or column. Because if not, then we would be violating the cancellation law that we proved earlier. So for instance, if say we have gi times gk equals gj times gk for some elements gi, gj, gk, then, well, we can do right cancellation, mimicking the proof that you would give for that. These go away, of course. So this explains why it's kind of like, what is it, like a Sudoku puzzle, how every element appears exactly once per row and per column. This is going to be a shorter video, so that's pretty much it for now. In the next video, we're going to look at further examples of groups, and maybe I'll throw in some example problems as well. Thank you for watching.